Dear students, in this lecture, we are going to see the characteristic wave impedance of TE, TEM and TM waves traveling between two parallel planes. First, let us look into the basic definition of characteristic wave impedance. This characteristic wave impedance, it is the ratio of component of electric field to that of the magnetic field. So ratio of E by H is nothing but the characteristic wave impedance in general. In specific, we can define the characteristic wave impedance as the ratio of electric field intensity along one transverse direction to the magnetic field intensity along the other transverse direction. So characteristic wave impedance is the ratio of electric field along one direction and magnetic field along the other direction. This characteristic wave impedance is represented as Z and it is given by the ratio of either Ex by Hy, that is electric field intensity along X direction and magnetic field intensity along Y direction, or the same can also be expressed as minus Ey by Hx. So these are the two ways in which characteristic wave impedances can be expressed. That is Zxy is Ex by Hy and Zyx is Ey by Hx with a negative sign. First, let us derive the characteristic wave impedance of TM waves. We know that for TM waves, these three field components will be existing. That is Ex, Hy and Ez. These three will be existing, right? And the equations for Ex and Hy that we derived in the previous derivation for TM waves is given right here. The equation for Hy is this, equation for Ex is this. This is the general wave equation for TM waves traveling between two parallel planes. Now, as per the definition for characteristic wave impedance, it is the ratio of electric field intensity along the X direction to the magnetic field intensity along the Y direction, Ex by Hy. So, Z0, that is characteristic wave impedance of TM waves, is Ex by Hy. By substituting the values of these two equations, Ex is this, Hy is this, Ex by Hy will cancel out all these components. C4 cos m pi by a x into e power minus j beta x is common in both these. It gets cancelled with each other and will be left with beta by omega epsilon. So Z0, characteristic wave impedance of TM wave is beta by omega epsilon. We also know that beta is given by 2 pi root of mu epsilon root f square minus fc square. The characteristics of TE and TM waves, we might have derived this. Now substituting the value of beta in the above expression, Z0 for TM waves becomes 2 pi root of mu epsilon into root of f square minus fc square divided by omega epsilon. Omega can be written as 2 pi f into epsilon. Now 2 pi will get cancelled with each other and we can express this as root of mu epsilon divided by epsilon square. We are taking this epsilon inside the square root into f square minus fc square divided by, if this f, we bring this f inside the square root, we'll get root of f square. So this expression can be written like this, in which we can cancel this epsilon. So Z0 of TM waves can be written as root of mu by epsilon into root of f square minus fc square by f square. So if I divide each term in the numerator by f square, I can write this as 1 minus fc square divided by f square. Now we know that eta, intrinsic impedance, is nothing but root of mu by epsilon. So this term mu by epsilon can be replaced by eta, and the expression finally that we get for characteristic wave impedance of TM waves is going to be eta root of 1 minus Fc by F the whole square. Now this is the equation for characteristic wave impedance of TM waves. Clear? The next is TE waves. Now we are going to derive the characteristic wave impedance of TE waves, and in TE waves these three field components will be existing. That is, we will be having equation for Ey, Hx and Hz. Only these three field components will be existing. So we know that the characteristic wave impedance formula is Z0 is either you can write it as Ex by Hy or minus Ey by Hx. Now since we have only Ey and Hx, here for TE waves, the equation for characteristic impedance is minus Ey by Hx. And these are the equations, field equations for Ey and Hx for a TE waves in general. So from this equation, by substituting these equations here in place of Ey and Hx, these terms will be cancelling with each other and will be left with 1 by minus beta, that is Z0 is equal to minus Ey by Hx. After the common terms are getting cancelled, we will be left with minus 1 by minus beta by omega epsilon. This can be written as omega mu by beta. This negative and negative will be cancelled with each other. That is what is written here. So now Z0 of TE waves can be written as omega mu by beta. We know beta is 2 pi root mu epsilon root of F square minus Fc square. By substituting this value of beta in the above equation and simplifying it, we get omega is 2 pi F into mu divided by 2 pi root mu epsilon root of F square minus Fc square. 2 pi gets cancelled with each other and you will get this as, if you bring this mu inside the square root, this term can be written as mu square by mu epsilon into F divided by root of F square minus Fc square. Mu and mu gets cancelled. So you will get root of mu by epsilon into, we can write this as 1 divided by root of F square minus Fc square divided by F square, by bringing this F inside the square root. So this can be written as root of mu epsilon into 1 divided by root of 1 minus Fc by F the whole square. As usual, this term, root of mu by epsilon is nothing but eta. So the equation for characteristic wave impedance of TE wave can be written finally as eta divided by root of 1 minus Fc by F the whole square. This is the equation, final equation. Clear? Next is the characteristic wave impedance of TEM waves. For TEM waves, we have Ex and Hy component. So the equation for characteristic wave impedance is Ex by Hy. These are the two expressions for Ex and Hy, in which these two gets cancelled when I substitute Ex and Hy in these two places. So we'll be left with only beta by omega epsilon. So for TEM waves, the characteristic wave impedance is given by beta by omega epsilon. We know that for TEM, and TM, beta is given by 2 pi root mu epsilon into root of f square minus fc square. But for TEM waves, this beta is given by omega into root mu epsilon. This is the expression for beta for TEM waves. By substituting this value of beta, we get the characteristic wave impedance of TEM wave as omega root mu epsilon divided by omega epsilon. Omega will be cancelling with each other. Omega epsilon, if I bring this epsilon inside the square root, it will be epsilon square, which can be further simplified as omega by epsilon. So, Z, that is characteristic wave impedance for TEM waves, is root of omega by epsilon, which is nothing but eta, characteristic wave impedance. Now, in this case, if we consider air as the dielectric, so for air dielectric medium, we know that mu is mu r into mu naught. Likewise, epsilon is epsilon r into epsilon naught. If air is dielectric, mu r and epsilon r will be 1. The value for mu r will be 1, epsilon r will be 1. So, we will be getting Z TEM, that is characteristic impedance for TEM, as root of mu naught divided by epsilon naught. Now, mu naught and epsilon naught are constants, right? And if we substitute the values of these two constants, this gets simplified as 120 pi, which is approximately equal to 377 ohms. So, characteristic wave impedance for TEM wave is approximately equal to 377 ohms for air dielectric. Otherwise, we can say it as this is equal to eta. Thank you.